Okay, so let's begin. So today I'm going to talk about magnetic scattering or neutron scattering and magnetic excitations, part 2. And this is a makeup lecture from the first one, which was interrupted. So let me start from the beginning. Again, my name is Young Lee from the Department of Physics at MIT. And here is an outline of the topics that we'll go over. And unlike the first lecture where we discussed excitations when you have a magnetically ordered ground state, which we called spin waves, we're going to discuss excitations from states that do not have magnetic order. And these are definitely on the cutting edge of current research in condensed matter physics. And neutrons have had a big role in understanding these types of systems. So let me first talk about one-dimensional systems, which are theoretically more tractable in understanding their physics, and I'll talk about spin 1/2 uniform chains. And then if you have a deformable lattice, so you can get spin parallels transition, and then spin 1 chains, which are sometimes called Haldane chains. Then let me talk about two-dimensional systems, in particular one that's close to my heart, spin 1/2 Kagami lattice materials, which do not have magnetic order as their ground state. And the last topic I'll mention is applying magnetic fields to induce ordering in order to understand better the spin Hamiltonian. All right, so to give you, again, the big picture overview, last time we discussed spin waves and systems with ordered ground states. And I talked about 3 different types of ground states in magnets. And these are ground states. They're in thermal equilibrium. And let's ignore effects of disorder or coupling to the lattice. Then you can get a ferromagnet state where all the moments are pointed in the same direction. An anti-ferromagnetic state where you have different sublattices of ordering. For example, here we have 2 sublattices that are pointing in opposite directions, so there's no net magnetization, but nonetheless you do have a well-defined ordered moment at each magnetic ion. And we saw that there were spin waves from both of these types of ground states. A new thing would be if the ground state did not have static moments, and such a state is called a quantum spin liquid state. And I will spend more time talking about what this type of state is. And it's quantum because due to just the quantum mechanical behavior of the spins, in particular low values of spins, you can get fluctuations that disrupt ordering. And this goes back to some things I mentioned last time about the anti-ferromagnetic spin Hamiltonian. So here is the Heisenberg model, where you have a coupling between nearest neighbor spins, and depending on the sign of this coupling constant J, if it's less than 0, then you have ferromagnetic interactions, and the classically expected up state here is also a good quantum eigenstate. But we saw last time that if J is positive, that tells you that neighboring spins want to be anti-parallel. And then, if you think about the classically ordered state, up, down, that turns out not to be a good quantum eigenstate. So up, down is not an exact ground state wave function. So something deep or something unexpected could happen for your ground state. And it actually depends on the dimensionality of your lattice, what are the possible ground state configurations. So let's look at this and let's consider what might compete with the up, down nail order, and we'll focus on spin 1/2. And it turns out that singlets, where you have pairing of spins that form a singlet, is a very good low energy state. So here is some simple math with trial wave functions. These blue ovals denote singlets between 2 neighboring spins. And let's consider, for example, in one dimension where you have a bunch of magnetic moments on a line. Now we can consider the ground state energy per spin, and if you just have up, down ordering, you're going to have a ground state energy that goes as s squared times z, which is the number of nearest neighbors, and also there's a factor of j. Now, if you consider a ground state which now is made up of singlets between nearest neighbors, such as over here, well, what you get is a factor of s times s plus 1, which comes from the quantum mechanical spin Hamiltonian, and it's also proportional to j. It's not, however, proportional to the number of nearest neighbors, because once you form a singlet with one neighbor, then that's your energy savings. So it turns out that for this calculation, the energy per spin is minus 3j over 8, which is lower than the nail energy, so singlets win. Now let's jump to 3 dimensions down here. And we'll just take a simple cubic lattice, and you can see that for the cubic lattice, you have more nearest neighbors per spin. So instead of 2 in one dimension, you now have 6 nearest neighbors. So you get a further reduction in your ground state energy. And if you compare that to the singlet calculation, well, the singlets don't scale with the number of nearest neighbors, so it's the same energy per spin. So that hasn't changed, but now the nail state is further reduced in energy, so this is a low energy state, so nail order wins. However, in 2 dimensions, it's not clear which state wins, so there should be some crossover between singlets being favorable to having nail order being favorable, and in 2 dimensions, it's not quite clear. And we can't rely on this simple type of calculation to give us the answer. And in fact, analytically, this was a big question mark for a while, even for the square lattice, which is what we say is a non-frustrated lattice. There's no analytic proof for the ground state being ordered or not. But we do have a lot of indirect methods to give us a sense of what that is, and I'll talk about that as we go along. So let's stick with 1 dimension where singlets are very favorable as the ground state, as we saw in the previous slide. And it turns out that this is for the spin 1/2 Heisenberg chain on a uniform lattice, that Hans Bethe, this giant in theoretical physics, told us what the exact ground state wave functions are. And you can think of this state, it does not have long-range order, and it's thought of as a superposition of singlets. You can also think of it as having short-range anti-ferromagnetic order, but it doesn't have long-range order. And something interesting happens if you look at the excitation spectrum. And here is a cartoon of what a fundamental excitation might look like. And in the middle here, I flipped a spin that used to be down to up. And this now creates 2 unhappy bonds with its neighbors, as shown by the black dotted line. Now, these black dotted lines are essentially can act as domain walls and can hop away from each other without a further energy cost. So I kind of drawn here those 2 unhappy bonds, and I drew a circle around where that occurs, and you have this domain wall between anti-ferromagnetic regions, and by further hopping these domain walls away from each other, there's no further energy cost. You just have these happy anti-ferromagnetic regions in between. Now what we've done is then broken up a fundamental spin 1 excitation into 2 types of excitations, which we call spin-ons, and they now carry spin 1/2. If you look at the excitation spectrum then, by having these 2 spin-ons, there are now, you open up a larger momentum and energy space to conserve momentum and energy, and that gives you a continuum of allowed excitations as shown in this diagram. So as a function of wave vector on the x-axis and energy on the y-axis, shown in red are the allowed excitations called the spin-on continuum. And what looks actually familiar is on the bottom of this continuum, you have this rather sharp lower boundary that goes up and it comes down to this pi over a position, which is the anti-ferromagnetic wave vector. If it was just having this single mode as the lower bound without the continuum, that would look like a spin wave. But since you do have this continuum of excitations above, this is different. So this is what's predicted in theory, and you can ask, well, what do neutrons have to say? And neutron scattering has been done early on these spin 1/2 chains to test some of these theoretical ideas. And here is some work done by Endo Shirani and company at Brookhaven. And they studied a compound, I'll just truncate with its initial CPC. This is a chain compound with copper running along the C-axis. And they write down the Hamiltonian in the following way. It's a Heisenberg nearest neighbor Hamiltonian. They have this factor of 2 in front. So this is how they define J. So J is known independently from other measurements to be about 13.4 Kelvin. So again, what's quite nice about one-dimensional systems, they have the advantage of being relatively simple for calculations, and in particular, the susceptibility, that is the uniform susceptibility that you can measure in a magnetometer, can be modeled very well with what's called the Bonner-Fisher model. And then if you measure the susceptibility, there's essentially no adjustable parameters, or just one, which is J. So you can extract J with no other adjustable parameters. So that's how you can determine what J is here. And then you can use that and predict what you should see with neutron scattering. So some of the early theory showed that there should be low energy excitations. This is theory by Desclozeau and Pearson. And the low energy dispersion relation goes as pi times J times sine of Q. And if you just did a simple classical spin wave calculation, you would get 2 times J sine of Q. So it looks, at least qualitatively like a spin wave dispersion, but the prefactor is different. It's larger. It's pi instead of 2. And that's actually very interesting and something that you should be able to see in an experiment. And here are some of the results. This is inelastic neutron scattering at low temperatures on this spin 1/2 chain material. And here are some of the raw data at different positions along Q star, along the L direction, the chain direction. And as they cool down from 80 Kelvin down to 1.3 Kelvin, they see a sharp peak in energy. So there looks like to be a well-defined excitation. And if they plot where this peak in energy exists as a function of Q, and this is again Q on the x-axis along the chain direction, energy divided by J on the y-axis, their data form these open symbols. And you can see that the top of this spectrum has the value of pi times J, which is this theoretical result. And it's definitely different than 2 times J, which would be the classical spin wave prediction. So this shows very early on that experiments can quickly verify some theoretical predictions, and there's definitely a synergy going on, and this is a recurring theme in a lot of work in magnetism and condensed matter physics, where neutrons have a very important role. Now, you saw these low energy excitations. They showed up as peaks in the neutron scattering. You can ask, well, are these spin wave excitations? They're definitely not classical spin wave excitations, but are they spin wave-like in some sense? And that was an open question in these early years of studying these interesting one-dimensional systems. And with some further neutron scattering experiments and some more in-depth analysis, they came to a conclusion about that question as well. And what they've noticed is that the scattering was very asymmetric as a function of energy. It seems like there's a sharp turn on as a function of energy at low energies, but then it just falls off more gradually at higher energies. And this is the magnetic scattering. And what they wanted to do is to understand what role the energy resolution of the spectrometer played. So they paid careful attention to modeling that, and they can compare, for example, the scattering from phonons, which are well-defined modes. And on the data to the right with the lines through it are sharp phonon modes with the line expected with the instrumental resolution, and they match very well. So if you had a sharp magnetic mode over here on the left, you would expect to get the solid line of scattering if it was instrumental resolution limited. But clearly the scattering doesn't follow this solid line. It has this dependence that drops off much more gradually at higher energies. So you can conclude that these magnetic peaks are not simple spin wave peaks. Rather, it looks like it's a lower bound, and there is some continuum of scattering at higher energies. So that was an important observation, and it helped understand the theory as well. And since those early days, there have been measurements on additional spin 1/2 chains with some more advanced neutron techniques. Here's some quite nice data by Tennant, Cowley, and co-workers on this potassium copper fluoride material. This is a spin chain material, and here's the dispersion. It's kind of rotated by 90 degrees with Q on the y-axis up here and energy on the x-axis. And they drew the spin-on continuum through 2 of the Brillouin zones. And what you see is this is done with a time-of-flight spectrometer. So they took trajectories shown with this solid line here, and where it intersects the spin-on continuum, as shown as these dark shaded regions, you should see intensity. And when they look at their data, they definitely see peaks of intensity where you expect to see them in the trajectory that they take, at least that they plot from their time-of-flight measurement. And this is showing you that in addition to having the sharp lower bound, you also have a sharp upper boundary, a well-defined upper boundary to the spin-on continuum as well. And these line shapes are now modeled with better theoretical fits to how the spin-on continuum should look. So there's a great deal of understanding now of the spin 1/2 chain and its excitations, and it is a spin liquid with a continuum of excitations. These spin-ons actually are sometimes known as fractionalized quantum excitations because you're fractionalizing the spin wave into spin 1/2 degrees of freedom. Okay, now that's if you just have a uniform spin chain. But what happens if you now have a magnetic system on a deformable lattice? And we know that the positions of ions can move, right? That's what gives you phonons, for example. And what happens is that on the one-dimensional chain with spin 1/2, there's a competing phase called the spin parallels phase. And this is actually the favored low energy state once you say that the lattice is deformable. So you can lower the energy by dimerizing the lattice. So I have a cartoon here. This is a uniform spin chain where you have up-down ordering, or you can think of this as short-range ordering in the beta ground state. And you can get a lower energy state if you dimerize a lattice. That is, you move every two atoms close to each other. So they form a singlet that's localized on the bond that's slightly shorter. Then you have a slightly larger bond between the second and third ion. And then you have a short bond where you form a singlet, a long bond, and then there's short bond over here where you form a singlet. And on every short bond, you form a singlet. So that gives you, so where you have a short bond, you have a slightly larger magnetic energy coupling, and that gives you a larger savings in magnetic energy. So the ground state is now an ordered array of singlets, and this is breaking translational symmetry because you have now spontaneously gone from a uniform chain to one that has alternating bond lengths. And what happens to the energy spectrum is that you now create an energy gap as shown here. There's a finite energy cost to creating an excitation out of this singlet state, unlike the uniform spin chain. And can we study this in a real material? And so one thing I should mention is that this should be the favored ground state for the spin 1/2 chain. However, there's another competing state, which is if you include three-dimensional couplings. So if you have couplings between chains, you can also enter into a three-dimensional Néel-ordered state at low temperatures. And that is often what happens too. But if you have very weak 3D couplings, then the spin parallel state should be the favored ground state. And is there a good material which this is the ground state? And I think one of the best inorganic spin parallel systems is titanium oxychloride, and it's titanium that is in the spin 1/2 state, which forms chains, one-dimensional chains. And here's a picture of the crystal structure. These blue ions are titanium, and if I just project that into the AB plane, it looks like so. And if you consider the orbital arrangement of the titaniums, you have this orbital overlap along the B direction. And that turns out to be a good one-dimensional strong coupling direction. And you could also see that neighboring chains now have this staggered arrangement. So they're staggered by half of a unit cell along the chain direction. So therefore, any coupling between chains is going to be frustrated. So this makes it a very good quasi-1D system. And there's a way of making single crystals of this with the vapor transport method and study the physics. So what would you expect if you do have a spin parallel ground state? Well, one thing that you should expect is that at some low temperature, once you dimerize the system and the singlets form, there should be a drop in the susceptibility. And in particular, this drop in the susceptibility should be isotropic. It shouldn't depend on the direction that you apply your field, because you just have a loss of the spin degrees of freedom at low temperatures. And this is exactly what we see when you measure our crystals. You have this loss of susceptibility along the A, B, and C direction that has the same magnitude of drop. So this is telling you that you have singlet formation below about 100 Kelvin. And then you can now ask, well, is it dimerized? And to say something about that, you want to do some scattering studies, either with neutron scattering. You could also do X-ray scattering. And I have this disclaimer down here that the next few slides will contain X-ray data. But the basic technique is essentially identical to neutron scattering techniques. I am going to talk about diffraction and inelastic X-ray scattering, which tells about the structure and the phonon dynamics and the spin excitations. So, one thing to keep in mind is, even though this is a neutron scattering course, there are complementary X-ray scattering techniques that you can use, and it's important to use the technique that can give you, the understanding of the physics of the material at hand. And in this case, the materials were so small that it was hard to do a neutron scattering measurement but since the X-ray beam is smaller, it allowed us to get sufficient intensity. So here is the lattice dimerization that we observed with X-ray diffraction. This was done at a synchrotron. And what you would expect if you have a uniform chain, well, then you would have a certain set of Bragg peaks. And once you dimerize the chain, you now have doubled the unit cell size. So you should get an additional set of Bragg peaks at 1/2 positions in reciprocal space. And we can call them superlattice peaks. So here's an example of that. Over here, we see that along this 0K0 direction at K equals 2.5 at 67 Kelvin, there is no scattering. But once we cool down below and down to 30 Kelvin, we see this very nice peak. And that peak is at the position indicative of unit cell doubling along the B direction, which is the chain direction. So this combined with the susceptibility result are very conclusive evidence that you have a spin parallels phase. You have singlet formation coupled with dimerization of the lattice. Now, you might have heard of spin parallel systems before, and there's been theory on spin parallel systems, but there's been some basic theory of how this transition should occur, and there's a fundamental prediction that has not been measured previously until X-ray measurements on titanium oxychloride. And this is a prediction for a soft phonon. So there should be a particular phonon that corresponds to dimerization wave vector that softens. And the idea is that you have these normal modes or vibrations of the lattice in the following sense. So these two atoms get closer and then further apart, and these two atoms get closer and then further apart. And then the frequency of this type of distortion goes to 0, so the distortion freezes in. So it's a very simple idea of how the dimerization transition occurs, but this has not been observed in a real material before. And the importance of this is that, to have a basic understanding of the spin parallel state, well, you need to understand what J is for your system, but you also need to understand the phonons and the coupling of the spin system to the phonons. And these two parameters, the phonon frequency and the coupling between the spins and phonons, have not been directly measured before, but it's something that our scattering methods, especially inelastic scattering, is really good for. And here are some of the data. This is now, again, X-ray data, but this is inelastic X-ray scattering taken with very high energy resolution. This was at sector 3 at the advanced photon source, so you can get energy resolutions of better than 2 MeV, which is on the order of thermal neutron scattering. So in fact, running the spectrometer is very similar to running a triple axis spectrometer. And we can do measurements at, these are constant Q measurements. So over on this side, I have labeled the K position. So this is the 0K0 direction. So this tells you where you are along the chain direction. And then I scanned energy. And at different temperatures shown here. So when you see a peak here, like such as this large peak at the bottom, that is coming from an acoustic phonon, and this slightly smaller peak at higher energy is coming from an optical phonon. So you're getting peaks similar to what you would see in a neutron experiment. And when you fit this to a damped harmonic oscillator line shape, you can extract gamma, so this would be the phonon width, line width, or the inverse lifetime, and the phonon position. And we compare our results at the different temperatures to lattice dynamical calculations shown in the green lines, and the optical modes seem to fit quite nicely. But there's a particular phonon mode, this is the longitudinal acoustic branch, that seems to be much lower in energy than the calculation. And this is a branch that looks like it's soft. When you get out to this 1/2 position, this is the zone boundary position, we see that the line width is very narrow at small q, but it gets bigger and bigger as you go out. So there's this anomalous broadening to the phonons as you go out, and that's indicative of this soft phonon coupling to the dimerization, this singlet formation in the spin parallel state. And that's very interesting. We can now just stay at the special wave vector of q equals 1/2 at the zone boundary and fit our data at different temperatures with the self-energy. Sorry, it's a little cut off. The self-energy that was calculated in theory by Cross and Fisher. And this is a very famous theory paper on spin parallels physics. And this gives us the width of this special soft phonon. And from it, we can now extract the intrinsic phonon frequency as well. So the lines in this top figure are fits to the Cross-Fisher theory. And then when we extract the phonon frequency, we see that this frequency drops down to 0, as you expect in a soft phonon transition. And that tells us that around 100 Kelvin is the spin parallels transition temperature, consistent with what we had seen previously. And another thing that we can extract is the coupling, just shown on this inset. We now know how strong the spin phonon coupling is as well. And this was a very important test of some fundamental theory that inelastic scattering of the phonons was a unique probe of. So that was the phonon system, and more recently there's been some really nice work on trying to study the magnetism with X-ray scattering. And what you can do is tune to one of the absorption edges of your magnetic ion, and you can get an enhancement in the cross-section. And this is called resonant inelastic X-ray scattering. So this has been done at the Swiss light source on titanium oxychloride. The one drawback of this technique is that the energy resolution is quite coarse. This is about 80 millivolt resolution. But if your coupling is large, then this might be enough in order to measure some gross features like dispersion relation. So here they're focusing on inelastic scattering, and it's in this yellow box. And if you plot where the peak is that they see, you get the dispersion shown on the right. Yeah. They can extract from this the nearest neighbor coupling to be about 90 millivolts. And this is at low temperatures. So you can figure out the weaker bond, the slightly larger bond length exchange constant as well. It's about 0.75 times J, the nearest neighbor, the strongest exchange interaction. So for certain systems, inelastic X-ray scattering is quite a powerful technique to measure the spin excitations, in particular for systems which are too small to measure with neutron scattering, just if the crystal growth isn't there to make big samples. All right, so that was a little bit of a diversion into X-ray scattering, but again, it's not that different than how we think about neutron scattering. And it's showing some interesting physics on the spin 1/2 chain. Let's go to now a spin 1 chain, and it turns out that you can get very different behavior compared to spin 1/2. So the spin 1/2 system, if you remember, just on the uniform chain, was gapless. This lower bound in the spin-on excitation spectrum went down to 0 at the antiferromagnetic wave vector. Now, it turns out if you have an integer spin, you have a gapped system. And the theory for this was conjecture by Duncan Haldane that these integer chains would be different than the half-integer chains, and that in the integer chains, they turn out to be gapped spin liquids, unlike the gapless spin liquid for spin 1/2. And this was a very important theoretical work, and neutron scattering was one of the early tests of this theory. So here's some work done by Bill Byers and co-workers on a spin 1 chain with anti-ferromagnetic interactions, cesium nickel chloride. And here on the left, I show the dispersion relation at low temperatures. And this does order eventually due to three-dimensional couplings, but there is a dominant coupling along the chain direction, along the C direction. But below about 4.8 Kelvin, it's Néel-ordered, and so what they're measuring in the figure to the left are spin wave excitations. Now, if you warm the system above the Néel temperature, then there you don't have 3D ordering, so what you're measuring then are fluctuations from the predominantly one-dimensional spin system. And that's what they're doing on these two figures on the right by warming up, and those are the closed symbols above the Néel ordering temperature. They're measuring predominantly the one-dimensional phase, and what they're seeing is that there's well-defined modes that have a gap. So they measured this at different Q vectors, and it's gapped. There are no gapless excitations, but you have these well-defined modes at these slightly elevated temperatures. So a spin gap is seen in the one-dimensional phase. And that is consistent with Haldane's conjecture, that you do have a gap spin liquid ground state. There's been some more work recently. Here's some work by Colin Broholm, Gabe Apley, and co-workers on another nickel-based spin chain compound shown here. And here is the full dispersion, and it's plotted as an intensity contour plot. So it's a function of Q and energy, and then these peak heights give you the intensity. So you clearly see it's also gapped. This does not go down to zero energy. And if you have a gapped system, you normally expect the correlations to decay exponentially, and you should have a short correlation length. So in particular, the equal time correlation length, if you integrate over energy, should be short. And they did a measurement of this, and shown in the inset here at different temperatures. So the open symbols are the energy integrated data, which gives us this instantaneous snapshot of the spin correlations. So therefore the width of the peak in this open symbol peak tells us about the instantaneous spin correlation length. And that peak is rather broad, and that's what you expect because it's a gap system. What was interesting is that you should have a longer range quantum coherence. And that's another feature expected for spin liquids, is that the quantum entanglement between spins is long range, even though the spin-spin correlations are short range. And as a measure of that, they've done inelastic scattering. So instead of energy integrating, they choose a fixed energy transfer, I guess they chose energy transfer of 36 millivolts, shown in the filled symbols here. And when you look at the peak for the filled symbols at low temperatures, it's very sharp. And this is telling you that you have a long-range quantum coherence for this ground state. And so, this quantum coherence is almost limited just by disorder in the sample. So it is very long range. So that was a very interesting observation. And one final observation by the same group is when they intentionally put additional defects into the material, so non-magnetic ions. So you're essentially splitting up your spin chains, and once you split a spin chain, you're essentially creating small segments of spin 1/2 Heisenberg chains, and therefore you have an end state near these impurities. It turns out that the end state should act like a spin 1/2 object, and these end states are actually very analogous to these topological states that are talked about a lot currently in these topological insulators, for example, where you have some bulk property, some bulk gap, but at the surface you have some additional state that's not that does not exist in the bulk, and that's the same thing here, where you have these spin 1/2 end states in the spin 1 chain, and they could measure excitations from these end states, and this is shown in this diagram. And what's interesting is that this is at the anti-ferromagnetic wave vector, so this end state is definitely due to anti-ferromagnetic correlations that propagate into the spin chain. And they talk about this as a way of doing, for example, neutron electron spin resonance. So this is a very nice measurement of this topological end state, again, where neutrons play a very important role. Okay, so that's in one-dimensional systems. Let's ask what can happen in 2 dimensions if you somehow get rid of the possibility of Néel ordering. And you could ask, can you get a quantum spin liquid state in 2 dimensions? And here's a picture of what it might look like. This is on the square lattice again, and Phil Anderson in the early days of high TC had speculated that this might exist even on the square lattice, and this would be a state where you have a singlet covering on this lattice, and then if you superimpose all of the different singlet coverings, that would be a nude ground state, a quantum spin liquid ground state. So such a ground state would not break conventional symmetries such as translational symmetry, and since there's no ordered moment, it does not break spin rotational symmetry. So this would be a very exciting new phase in 2 dimensions. And I also drew, if you broke apart one of your singlets, you would have these free spin 1/2 objects that are free to propagate away from each other. And these are the 2-dimensional analogy for the spin-ons that we had talked about in 1D. So you could ask, can you see spin-on excitations in 2 dimensions? That would be very exciting. So a goal would be, can you find such interesting ground states in simple systems, so regular lattices? And if you want to have a hope of doing that, you want to look for this in materials made up of triangles, because a triangle with an anti-ferromagnetic interaction is frustrated. And you can see that here, where you have 2 spins anti-parallel on this bond. So there's an up spin here, a down spin here, but this third vertex of the triangle cannot be anti-parallel to both. So it's frustrated. And then you can ask, well, what types of lattices can I make from triangles? You could have an edge sharing network, which we call a triangular lattice, or you could have a corner sharing network, which we call a Kagami lattice. And it turns out that Kagami lattice is more frustrated. It has a much higher degeneracy of classical ground states due to the frustration. Therefore, Néel order is less likely to occur. And in particular for spin 1/2, it's not expected to have Néel order, and you could have something else. And that is an important question theoretically. It's a very hard problem to get analytic results for, but there is a general consensus that the Néel ordered state is not the ground state. But you could ask, well, what is the ground state? Is it a spin liquid, which would be very exciting? And there are many different types of spin liquids. Some are gapped, some are gapless, and there are different proposals. And recently, David Hughes and Steve White and co-workers showed in Science that they used DMRG methods on large lattices to indicate that the ground state looks like a spin liquid with a small gap. But there are other possibilities that are not spin liquids called valence bond crystals, and this is where you more or less localize the singlets on certain positions in the lattice, kind of like the spin parallels phase, but this can now have a more two-dimensional pattern of where those short bonds exist. And this would be more conventional, not as interesting as having a spin liquid state. In theory, it's hard to understand precisely what the ground state is. Can the experiments tell us something? And this is where some work that I've done with Dan Nocera's group at MIT comes in. We studied a compound called Herbert Smithite, and the main idea is that the copper ions in this compound form this ideal Kagome network, and you have non-magnetic zinc layers separating them. And I guess you can look at the structure here where you have this blue Kagome network, and red are the zinc ions that are non-magnetic separating them. So it has a rather ideal Kagome structure. So if we can study the spin excitations in this compound, we should have a good idea of what the ground state for these spin 1/2 Kagome lattice should be. So the linchpin experiment would be to do inelastic neutron scattering on a single crystal and to look for unusual excitations such as spin-ons in a two-dimensional magnet. That would be rather unprecedented. Now this is a hard experiment because first you're dealing with spin 1/2 and the inelastic cross-section is proportional to your spin value. So spin 1/2 is the smallest, and it will just be a very weak signal. In addition, these are not spin wave excitations, which are sharp in energy, but these are continuum-like excitations, which are broad. So there will not be sharp peaks in energy or Q. So when you don't have sharp peaks, you're spreading out your intensity over a larger phase space and momentum and energy, and it makes it harder to measure above background. And the last roadblock is that in the beginning there weren't recipes for crystals. And you can say, well, crystals are not, the ability to make crystals are not, a neutron, scattering technique roadblock. But I would say that growing crystals and doing good neutron experiments are becoming more and more related, and you should value the ability to make crystals because that can be the difference between success or failure in a neutron experiment. So we spent a lot of time trying to make crystals. And we essentially had to invent a new technique for doing this. So this is work by my grad student, Harry Hahn. What we essentially ended up doing is making a gradient in a tube furnace and putting all the materials in this aqueous solution, sealing it in a quartz tube, and putting all the starting materials on one side and then having them transport slowly over time to a cold side where we could make large single crystals. And this crystal growth took many, many months to grow just a single piece, about 10 months from start to finish. So it's a very slow process, but it was definitely worthwhile because it led to the success in the neutron scattering. In addition, again, we said there are many roadblocks for this experiment. You want to have really cutting-edge instrumentation to be as efficient in your data collection as possible, and that's where this new instrument called the Multi-Axis Crystal Spectrometer, or MAX, at NIST, this was pioneered by Colin Broholm, was instrumental. So in this type of instrument, you have 20 different analyzer detector channels, and this is the analyzer housing shown here. So you can stay at a fixed energy transfer and very efficiently measure a broad reciprocal space associated with that energy transfer. And the nice thing is that for measuring spin-ons, again, we don't expect there to be sharp peaks, so being able to reduce the background as much as possible is key. And having an instrument like this MAX instrument that allows you to have collimations between your sample and your analyzer allows you to reduce the background from these stray neutrons or incoherently scattered neutrons. And that was definitely key. So having the ability to do experiments in different types of spectrometers, for example, not just time-of-flight spectrometers, is important, just to have a different suite of available techniques. So here's some of the data, and we measured the background from an identical sample holder and then subtracted that. So this is all scattering that is coming from our crystal. And here's the energy transfer of 0.75 millivolts, 2 millivolts, and 6 millivolts. And this is, the intensity is proportional to S of Q and omega. What you can see is that the scattering, and most of the scattering that you see in green, this is all magnetic scattering. There is some scattering from phonons that occurred near the 3D structural Bragg peaks, and for example, this red out at the edge here and here are related to the phonons near the Bragg peaks there. But this green scattering here is magnetic. So this scattering is, definitely it is stronger than just coming from, say, impurities in our sample. So this is intrinsic to the Kagame spins. In addition, what you notice, it's very diffuse scattering. If you look, for example, in this top panel, the width spans a large fraction of the Brillouin zone. These are not sharp delta function in energy surfaces. So it's very different than spin waves. And being very different, it's quite exciting. You can now take cuts and plot it as a function of wave vector and energy along different directions. Here's a trajectory plotted down here for one of the cuts over here. And you see as a function of wave vector and energy, you get this essentially like a wall of scattering plotted this way. And again, you don't see a sharp single curve for the dispersion. And this is consistent with having a continuum of spin excitations in a two-dimensional magnet. I should also mention that we're measuring at very low temperatures compared to J, about 100 times smaller temperature scale, 100 times smaller energy scale and temperature than J. This is not disordered due to thermal reasons. What we have is a quantum disordered ground state or spin liquid state. All right, so just going back here. So, again, this is very strong evidence from neutron scattering of a new type of excitation in a quantum magnet. There's, definitely a lot more for neutron scattering to tell us about the research in these interesting quantum magnets. Now let me take a few last slides to talk about, well, you can measure some interesting excitation, and that is the ground state, those are the excitations from the ground state in some particular system. But what can you say about what that system is, right? I kind of summarize that as well. We have an answer. Now, what was the question? We can measure some novel excitation in a real material, but if we don't know what the underlying Hamiltonian is, we don't know what this is telling us, for what model this is the excitation spectrum. So what is the spin Hamiltonian? And that's kind of a conundrum, right? We want to measure spin wave excitations because, as we saw last lecture, the spin wave excitations give us a lot of information about the Hamiltonian parameters, right, such as the exchange couplings or the spin anisotropy terms. But what happens if you have a magnetic system that doesn't order and therefore allow you to measure spin waves? One interesting technique that you can do, and this was work by Caldea and co-workers, where they measured interesting excitations in this cesium copper chloride 214 compound. What they observe, this is a spin 1/2 compound, they observe what look like, or what are continuum excitations, and it's due to the spin 1/2 coppers. So you have this exotic spin continuum seen, but you could also now ask, well, what is the underlying Hamiltonian? Is it of a more 1D nature or 2-dimensional nature? And looking at the crystal structure, this looks like it's kind of caught in between 1 and 2 dimensions. There are these chain-like features, but there's also coupling between chains. And to get the particular exchange parameters, it's hard to extract just from the spin-ons. So what they did is applied a large magnetic field and they polarized the system. So they have an effective ferromagnetic state, and from that ferromagnetic state you can measure spin waves, and the dispersion of those spin waves tell you the various exchange parameters. And so here, when they apply a large field here, they see, instead of the continuum scattering, they get these sharp spin wave modes, and they can fit that to extract the parameters in the Hamiltonian. And here's another example of this technique where you apply a large field to get the parameters in the spin Hamiltonian. This is work by Kate Ross and Bruce Golan and co-workers, with theory by Leon Balance's group. And this is an interesting pyrochlore system. It's one of these compounds that are believed to be spin ice-like, where you have spins on corner-sharing tetrahedra. And I don't want to go into too much of the details, but you could write the Hamiltonian in the standard way, where you have some global axes, x, y, and z, and then you have this exchange tensor with your spin interaction. But there's another way of writing the Hamiltonian which relies upon local axes, and this is how they write it here, so you can extract different parameters for this as well. And what they did is, by applying large magnetic fields, so here's 5 Tesla, here's 5 Tesla data, 5 Tesla calculation. They also have 2 Tesla data and 2 Tesla calculations. They can now extract what these relevant terms are by doing a fit to the spin waves. So they get very detailed understanding of the spin Hamiltonian, and they believe this compound is a good realization of a different type of quantum spin liquid called quantum spin ice. And what they see in zero field does not have spin waves, but has something else, which looks to be more exotic. Okay, so that's coming to the summary, the last slide. So there are many exciting, novel excitations on quantum magnets. This is forefront research in condensed matter physics, and neutron scattering is one of the most important probes of this. And historically, neutron scattering has been involved early and often in understanding the excitations. And there's a clear synergy with the leading theoretical ideas, which make, I think, it particularly fun to be involved in these neutron scattering measurements. So that is the end of the lecture for today. All right, so thank you, and I guess that does it.